All right, I believe that I'm sharing my screen. Looks like I'm sharing a little more than, there we go, than I'm trying to. Great, so my name's Josh Johnston. I'm a Vice President of Engineering at Count, and I'm gonna be talking today about artificial intelligence at the human interface. This is going to be a fairly high-level talk. I'm not diving into a lot of technical details of data science or artificial intelligence. So this talk is more oriented around how to run a successful artificial intelligence program as part of your business, or how to be successful as a data scientist or somebody working in the artificial intelligence space, data engineering, machine learning engineering, et cetera. So first, just a little bit about me. I came into the AI field via robotics. Back in the day, AI was just part of robotics. There wasn't like a separate space for it. So all of us who were doing, who were doing AI in the robotic space. So these are some of the vehicles that I've worked on. Not sure how the video is going to work on this platform, but this is a very slowly moving there up on the top center of the screen. You can see this is a vehicle called Scarab that I worked on in grad school. We developed this as a mission concept for a rover that would explore permanently dark craters on the south pole of the moon, looking for water ice. This red Humvee here is called Sandstorm. This was a vehicle that I also worked on in grad school for the DARPA Grand Challenge, which was a vehicle race across the Mojave Desert. I'm driving that really, really dirty Ford Explorer that's behind here. We put about 4,000 miles on that. It was a rental car, and we returned it, and just about every idiot light was glowing on the dashboard by the time we took it back. Felt a little bit bad about that. But this is back, the very early days in self-driving vehicles. We didn't call them self-driving vehicles back then. We called them autonomous vehicles or robots. It's kind of funny looking at some of this video now. This was in summer of 2005 at the Nevada Automotive Test Center outside of Carson City, Nevada. And this was like nuts at the time. Nobody was doing this sort of thing. And now it's just kind of, well, obviously a car can drive down a road. This is happening all the time in much more challenging situations than this. But this represented an order of magnitude increase in the state of the art. So the year before this, here we're driving at 35 miles an hour, missing traffic cones, and had a mean time between failure of over 200 miles. The previous year, the state of the art was 7 miles, and the speeds were not as fast. So, this field can move very, very quickly in when it gets going. After I left this robotics space, I spent a couple of years at Boise State University as a research scientist. One of the things I did there was working on augmented and virtual reality. Again, kind of back before it was cool. So this is an augmented reality. This is viewed on a phone. And it's an interactive map for a project that I did with Idaho National Labs, visualizing usage of electric vehicle charging stations in the Pacific Northwest. Back when we were doing this, like nobody had seen augmented reality before. This was before Pokemon Go and kind of the revolution for this. Our sponsor over at INL, she showed this to somebody and they said, "You're a witch." That was kind of what their reaction was like back then. A lot of these things have been much more mainstream though. For me, this was kind of an extension of work that I had done with these other vehicles that look like, they're bomb disposal robots. So I worked visualization, building real-time 3D models for visualization for explosive ordnance disposal. And then the bottom left, there's a vessel called Sea Hunter, which kind of completes the air, sea, space, ground. It completes that sea space for me, which it's a built-for-purpose autonomous vessel, another DARPA program. And specifically on that, I worked on the electro-optical infrared system and developed the requirements for that. So that's my background. I bring a lot of biases as a robot guy. The folks here at Count will tell you that I tend to still think about things as if they're robots. You'll see that in this presentation, but at least in my experience, it's been a helpful lens to look at. So the first question is, you'll notice I've said artificial intelligence a lot. I haven't said machine learning. I want to talk a little bit about the terminology here, because it's important for the idea of deciding what you're about and what problems you're actually trying to solve. I'll start by saying that none of those vehicles that I just showed on that previous page had any machine learning in them. So first, I want to go after the myth that artificial intelligence requires machine learning, or even that machine learning is a subset of artificial intelligence. These are distinct concepts that do have a lot of overlap, but they're not the same thing. So what is machine learning? It's simple. It's the ability of a computer to learn without being explicitly programmed. You don't have to have neural networks. You don't have to have something that's super complicated. Anything where the machine is learning something without being, without being exactly told, that's machine learning. The primary method that we use for this is a model. And I want everybody, I'm not going to make people try to answer me here, because I've got Nate Monig in the room, and he's the only person, I don't want to put him on the spot or deal with the trying to get somebody up here on Hopin on short notice. But I want everybody to think, what's a model? Like, if you're working in this space, machine learning, AI, you probably talk a lot about models. Well, I think it's funny, because I was at Boise State with a group of a dozen faculty members, and all of us, I think, described ourselves as modelers of one type or another. And somebody asked the question in this meeting, they said, what's a model? And like, all of us just kind of looked down at our feet, because we had no idea how to define this. So I went and actually thought about it a little bit. Sorry, I lost my mouse here.
It's a simplified representation of reality.
So Nate says it's a simplified representation of reality. There's definitely an important aspect, which is that it is a representation. And this is the definition I like. It behaves like a real system in one or more ways. So it actually doesn't have to be simplified. And that's, there's this quote here by Norbert Wiener, and I love the quote. I also love the name. Norbert Wiener, he started the field of cybernetics, which is the study of control systems, very important in the robotics and AI space. And he said the best material model of a cat is another, or preferably the same cat. A model is a representation of a real system. Usually, though, when we want to use one, when there's an advantage to using one, it's because it's cheaper or simplified, it's faster, or has some other kinds, it's safer, has some other kinds of advantages over observing the real system. This is an example here of an aerodynamics model. Again, I tend to think in physical systems and not in the abstract virtual world that I spend most of my time in. This model does not represent an airplane. It's not all of an airplane. It's not the right size. It doesn't have landing gear, avionics, or a place for people to go. It's only an aerodynamics model. It represents the aerodynamics very accurately, and that's the only thing it's supposed to represent. If you were building an airplane, you would also have other models, like a landing gear model, which would look something like a big landing gear sitting there with a weight on it probably, and some kind of a mechanism to induce forcing. Similarly, there's a mock-up somewhere of what it looks like in the cockpit and what it looks like in the cabin. But each one of these is only representing the real system in a single way. So at Count, we help merchants by protecting them from online credit card fraud. So to try to make this real, what I mean by a model, on the left side of this, we see the pattern that we're trying to identify, which is a fraudster goes and buys something from a merchant, and then later it becomes a chargeback, which is what happens when a charge shows up on your credit card that you don't think is supposed to be there. You dispute it, and if you're right, because a fraudster used it in this case, then that becomes a chargeback. The merchant has to pay the money back, and obviously they don't like to do that, so they pay us to help reduce their risk and liability. Now, this process on the left can take about 3 months, because first you have to look at your credit card statement, which some of us take a while to do or don't do every month. And then you have to initiate the chargeback process, and that takes time to resolve. So the real world process is slow. We want to get there faster. And that's why we do this stuff over on the right side, which happens in about 250 milliseconds. We collect some data from the merchant, from the transaction. We convert that data into features, which I'm happy to talk about that distinction, but I don't have it planned. I've got a backup slide on that if that's something we want to talk about at the end. But these features are a way to think about the data that is generally more mathematically aligned with what the model's expectations and assumptions are. And also oftentimes it's a way to inject expert knowledge into this system. We have a model, and then we get these results. And the idea is that results should be the same as the 3-month process on the left. We should get the same answer, but we should get it in 250 milliseconds. And that's why we have a model. Now, it doesn't represent the entire system because we're not trying to evaluate whether somebody's going to be happy with their purchase or be a repeat customer or anything else about this transaction. We're only trying to reflect the fraud. That's the only part that we're trying to look at. And then the kind of green arrows show the evaluation path. There's this training path that comes back the other way. And this is the way of thinking about how we actually build this model and these features in the first place. There's a feedback loop to train the model, to oftentimes train the features. And technically this can go all the way back to collecting different data, but that's oftentimes not automated. So this is what we mean when we're talking about machine learning and this model being able to learn without somebody going and explicitly programming it. So this is a machine learning solution to this problem. If you haven't seen this XKCD comic, then you haven't been listening to a bunch of AI talks. But this is perfectly describes what we do. This is your machine learning system. Yep, you pour the data in the big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. And this feedback loop with the training, that's the stirring the pile. Now, you think about it, there's some structure to the model itself, but then there's also a structure to the learning algorithm. And the difference between learning algorithms, machine learning models that we use is primarily a difference in how this training happens. So what heuristic you're using to stir the pile so that it's hopefully a little bit better than standing there with a paddle and stirring it manually. So machine learning has had a whole lot of hype over the years. I like looking at the Gartner hype cycle. This is very subjective. They do pretend that there's some measurements behind it. But the hype cycle is this idea that people will talk about stuff, they will inflate the expectations, then you drop into the trough of disillusionment, and interesting things start to happen. People seem to think it's a bad thing to drop into the trough of disillusionment, but that's where actual value gets added. Before that, it's inflated expectations and hype. People that are really getting work done tend to be working in the trough of disillusionment and up the slope of enlightenment. So in 2014, machine learning had not hit peak hype. I think we can all agree with that. And by 2015, the hype around machine learning had peaked. No, actually, in retrospect, that doesn't make any sense. Gartner thought that it had, but then in 2016, it turned out that there was actually still some space left for the machine learning hype. It's moving back up to the peak of inflated expectations. By 2017, it was still there. And in fact, they were like, no, maybe there's a little bit more left to go. 2018, they finally decided that we were past it. And then mysteriously in 2019 and 2020, machine learning disappeared from this hype curve entirely, which I guess is the ultimate trough of disillusionment. So yeah, lots of hype around machine learning. I honestly think that a lot of money has been spent without much more idea than this guy's got right here. You have data, you read in the magazines about how you're supposed to extract value from your data, and you hear machine learning is the way to do that. So you're gonna go after it. There's obviously a lot of problems with that, ways that this hasn't worked. I'm gonna address how I think you get around this. But I also do want to call out specifically one of the particular problems we have with machine learning is that it tends to be a black box. And this can be a problem for coming up with a good solution, but it's also increasingly being a problem if you're in a space that has issues with compliance and governance, if you're concerned about biases and discrimination, or if you're concerned about systemic risk that needs to be understood. We work with a bunch of large banks. They're regulated in a way to try to keep the next 2008 financial crisis from happening. And I think increasingly you're going to see challenges with machine learning, even when you can prove that it works better than the alternative, because you can't characterize necessarily the systemic risk or these external risks or externalities in terms of impacts like discrimination and unfair bias. So artificial intelligence, right? This is another comic I like out there. I think it's a good laugh. I think this accurately reflects what a lot of the field thinks about machine learning and artificial intelligence. Statistics is just kind of this thing nobody wants to deal with or address, but you dress it up and it's machine learning, and then you call it artificial intelligence wants to watch you do it. Again, I think that this is a misunderstanding of the relationship between artificial intelligence and machine learning. So to hit that on, what's artificial intelligence? Artificial intelligence is a machine exhibiting human-like decision-making. If you go back to Alan Turing's test in the imitation game, the idea is, he said, let's not talk about what intelligence actually is. Let's just say that if you can't tell the difference between a person and a machine executing a particular task, then we'll say that the machine has human-like intelligence. One of the really interesting things about this definition is that it is subjective, it's experienced by the person, and it changes over time. So if the intelligence is something that you expect from a computer or from an animal, then it won't strike you as being artificial intelligence. And the example for me of this, another good XKCD, when I was in grad school, I took a class in artificial intelligence because you had to take the class in AI or machine learning. And today everybody would take the class in machine learning and learn about neural networks. And back then, 2005, 2006 timeframe, machine learning was really just about optimizing parameters in control systems. A lot of classical controllers and not very interesting stuff. But artificial intelligence was a very active and interesting field at the time, but it was all algorithmic. Yes, we talked about machine learning algorithms and we applied machine learning algorithms, a lot of Bayesian algorithms, very much more heavily statistics based than we are today with neural networks. But the field for a long time had been focused on playing games, and chess in particular had been the metric for a long time. I remember when I had a chess game that I could beat consistently on the most difficult setting. Well, then in 2005, when I was taking this class, that was the last time that a human was able to beat the top chess playing machine in the world. And we talked in that class about how that means that chess was basically no longer an artificial intelligence problem. It was now just something you expect computers to be good at. And we see this where now my kids say, of course your phone can beat you at chess. It's a computer. Like, how would you beat a computer at chess? So over time, we call this the AI effect. Artificial intelligence kind of gets defined down into a smaller and smaller set of problems. What I find particularly interesting about this is that this comic was made towards the end of 2013, and it puts Go as the furthest out challenge, other than the jokes down at the bottom. And this was something at the time we thought was probably 20 years away, maybe never, that computers would take the top human grandmasters at Go. And instead it was 2016. It was barely 2 years later that AlphaGo beat the top human grandmaster. So you can see this and say this is a weak definition for artificial intelligence because it's always going to be changing. I actually find it to be useful because, and this is the point, right? This is the title of the talk, so this is the part you pay attention to. If I've already bored you to not paying attention, AI is defined at the human interface. So it's an impression that the user has of the system. That's how we define artificial intelligence. It's fundamentally a user perspective. This matters a lot when you're thinking about product design. I've got Google and Google Assistant here. If you're looking at that search bar and you think about how you would use the search bar, your brain is already probably wiring into thinking about how to run a search. You put in keywords, you leave out a bunch of other words. You don't try to make, syntactically correct sentences. You leave out words that you think might bring up something that's not relevant to your search. You might start thinking about exclusions and other rules that you want to put on this. No matter how good the search team at Google is, no matter how good their recommendations that they develop, you will never be fooled into thinking that you're talking to a person. This search bar essentially cannot achieve artificial intelligence because you are being forced to translate in a very non-human way, and you're putting yourself mentally into the space of the machine. In contrast, Google Assistant, right now it kind of sucks. So nobody's going to be fooled into thinking that there's a person on the other side of it. But you can see that from a product design standpoint, that it is achievable to have artificial intelligence here. If you make the back end of this good enough, somebody will not know whether they are talking to a computer or to a person. And that means that there's a reason that everybody's putting out these assistants. And it's not just because they thought, hey, here's some cool new technology. This is looking forward and realizing that people don't want to have to think the way a machine thinks. They want to think the way that a person thinks, and they want the machines to meet them on their own terms. And thinking about artificial intelligence in this way is I think, valuable in helping direct the way that you think about product design and product development. What this meant for us at Count, we used to have two different machine learning scores. One was based on a real-time network linking approach, which was unsupervised, meaning that there is no outcome data used to train those machine learning models. And then we developed a supervised model that does use the outcome information. And these were presented to the customers as two different scores, and we had a lot of issues around that. We also started thinking about some other things that we wanted to put together. And again, Nate Monig, who I've got in the room here with me, we got to this point where I was saying we should add this third score. And Nate's like, so you're spending a lot of time talking about all this stuff I've just said about artificial intelligence and people wanting to interact with something the way they'd interact with a person. And now you're going to go shove another score at them. This is not how a human fraud analyst would address the problem. So we pushed ourselves into developing a single score that incorporates all of the value of our machine learning. And we called that the OmniScore. That was our internal name for it. And then product marketing didn't come up with anything better. So they used it externally. And an OmniScore is actually our best guess. It is what a human would do, pulling all the information together. Now, this wasn't easy. There were a tremendous number of technical challenges that we had to overcome in order to be able to build this score and do it within the 250 millisecond response time window that we have. So, I don't want to act like this was just, and then we had an insight and the problem was solved. But this gave us motivation to put all of that work in to actually build this single OmniScore. And I was, one of the great, I think, accomplishments of my career was listening to the Q1 earnings report for Equifax, which is a multi-billion-dollar company. And as they were talking to their investors, they showed the data that Equifax has that nobody else has. and Count OmniScore was listed on there. So there's a lot of value in this, and the way we got there was by thinking about the most customer value being something that looks the most like a human intelligence. So we have an AI vision at Count that says our products feel smart enough that customers expect there are humans behind them, and performance is better than if there were. Now, this is obviously aspirational. I don't think that anybody right now is fooled into thinking that there is a person behind our products. But this kind of a vision can be a helpful guiding principle because, again, it has led us to make decisions in ways that get us closer to this aspiration. And I think that's been important versus being focused on technology. If you look at this vision, it doesn't say anything in here about machine learning or about the technology. Now, obviously, we're still technologists and we have to deliver on this promise using technology, but I don't think our customers really care. They care about these results and they care about the way the interaction feels. So this leads us to kind of three things that we have focused on to get to this vision. One is this AI-driven decisioning. Realizing we're not trying to produce a bunch of scores and show them a lot of scores that the customer has to synthesize into an answer. We are trying to provide a decision. That was a fundamental shift to the way Count thinks about our product. We used to deliver a SaaS framework. There's a software solution. We have a whole bunch of data in there. And it's basically a workbench. You can come in and you can write rules and set your policies. And that was how you found fraud. We've switched that thinking to the idea that we are actually delivering the decision. And we still allow our customers to write rules and to set their policies. But the intention now is not that they have to do that to find fraud. The idea is that they are doing that to make adjustments at the margin for places where the machine learning is still failing to identify fraud correctly. But more importantly, for being able to set their own policies and preferences for risk appetite. The superhuman results, that's really has to be driven by our technology, right? If it's not as good as a person, or if it's only as good as a person, then we're at this point where we're saying, yeah, we can, reduce your costs by cutting some fraud analysts out of your budget. And it's a very difficult space to be in to try to sell your product on the basis of eliminating a few not very well paid positions. So the real benefit here is to exceed human ability. And finally, we have to be able to provide evidence. I talked a little bit about that idea that machine learning as a black box is a challenge. It's a problem when you're trying to sell customers on that you actually have a viable artificial intelligence solution. You need to be able to show them something about how it's going to work. And I said that AI changes over time. If it was easy, it wouldn't be AI because we just say that's something that a computer can do really well. So I like these pictures because I like robot stories. When I was at Carnegie Mellon, in the 2004 DARPA Grand Challenge, we rolled over the vehicle on the top there, Sandstorm, a week before the race. So there it is upside down a week before the race. The picture on the right is at qualifier about a week later. And that was rough, whole lot of hard work. And we didn't get the calibration right. So it was still impacted by this rollover event. So the next year we organized everything around not rolling the vehicle over a week before the race. And we added a second vehicle, Highlander, and that's Highlander rolled over a week before the race. We actually gave ourselves a couple of days less the second time around. Completely smashed up everything, broke the suspension. We got it rolled over. We had to pull all the electronics out of the inside to get rid of the engine oil that was all over the inside of the vehicle, and to jack the roll cage back up roughly into place with a hydraulic jack. I remember distinctly sitting, leaning into the passenger side, using an 8-pound short-handled sledgehammer to pound the roof roughly back into shape on a $120,000 luxury vehicle that we had turned into something that drove itself, while sitting out in the middle of nowhere in Nevada. And I just remember thinking, they're actually paying me to do this. That was awesome, right? Well, it was hard. We had a huge team of people. And from the picture on the left there to this picture on the right, which is this vehicle driving itself autonomously, was less than 48 hours. You can see the shadows are longer on the left than they are on the right. Less than 2 days later, it took us about a day to get it running again, to get the engine running, drain all the oil out of the cylinders. Had to put it on the alignment table after we rebuilt the suspension. Had to pound the roof back into shape, put our spare roof rack on and all of our other spare parts. And then a day later, we had it driving with perception and route avoidance. So AI, these projects are really hard. And if you want to be successful, I think you have to think about, why do we fail at these projects? Again, I think about things as robots. So we have the same kind of argument in the robotic space as we do in AI and machine learning about how do we even define what it is that we do. So there's always been a big argument about what a robot is, what makes a robot, and various different ways to do this. The paradigm that I like the most is the idea that a robot has three major components: perception, thinking, action. And it has to have all three of these components to be a robot. And then I further put, whoops. Sorry, I'm trying to get my top-end view up. I further put the world in here, because the world is sort of the implicit actor here. You're perceiving the world, thinking about it, and making some kind of adaptation that has to have some level of complexity based on the inputs. It's not just a simple stimulus response. And then you take actions, and those actions affect the world, which then changes the perception of the world. So this means things like arms that are doing manipulation, or a car that you're driving around. These are places where there's action, and then the perception is going to change because the world has changed. So if we look at a couple of examples, again, thinking about robots, this is a computer. You can tell these slides are a little bit old because of how old the computer is. A computer thinks. You can run very complex algorithms on it. It doesn't really have a mechanism for perception or action, so we don't consider it a robot. Now, again, as I said, the slide's a little bit old. I think that we're increasingly being able to make the argument today that a computer that's internet connected actually does have the ability to function as a robot with a complete closed loop. I can go and set a buy order on a stock and say, when the stock goes below a certain price, I want to buy it, and that happens, and there's real money changes hands. I can go buy things on the internet using my refrigerator. So I think that the barrier here is coming down. But again, bad case makes bad law. So in general, we're really only thinking here about the computation. Sometimes people ask, well, does like a self-opening door, is that a robot? Because it definitely has a lot of components of a robot. It does have perception. It does have action. Again, we don't consider this a robot because it's just a stimulus response. There's no real complexity to what's going on. So this is, again, a self-driving car. This was a vehicle called TED from a team that I led in the 2007 DARPA Urban Challenge, which was the first place where people tried to really solve traffic laws. And these days, the Urban Challenge is seen as like the founding myth of the self-driving car movement. It was really where things got kickstarted and got heated up. Everybody asked us what TED stood for, because it seems like something that should stand for something. We never told people what it really meant, which was at a PF Chang's in Princeton, New Jersey, with one of our partners. We were trying to figure out, we actually at the time were planning to have two vehicles, and we were trying to figure out what to call them. And we decided to call them Bill and Ted, because it was either going to be an excellent adventure or a bogus journey as we built this out. So people of a certain age will get that one. This does meet all of the requirements, right? You can see the sensors all over it. There's complex perception. There's complex behaviors and thinking. Again, not driven by machine learning, still meeting the definition of artificial intelligence. And then there is action. because it can go and drive. And if it runs you over, then you're not going to argue that it doesn't have an impact on the world. So that's robots. What does this tell us about business? I think this is the right way to think about your projects. Anything that you're doing as a data scientist should have all of these components. Otherwise, you're probably not really adding the value that you could be adding to the organization. When I first started talking about this several years ago, everybody was trying to jump into the think space. They were saying, we're going to hire data scientists, and those data scientists are going to be super smart. They're going to have machine learning. They're going to be that guy with the data machine learning, awesome. And then we found data scientists were showing up, and it turned out the data was not really available, or it wasn't in a usable form. So they spent all of their time developing the pipelines to get the data into a usable form. I think we've solved this problem now in most places. Yeah, I'm sure there's still people who are walking into this trap, but there's been an increased focus on machine learning operations, data engineering, realizing that there's a lot of work to get the data into a usable state before you can go and start doing this thinking step on it. So that's been improvement, but where projects are failing still is in the action. And if you think about a product-oriented data science team like we have at Count, where we're building a product and selling it to our customers, that action is very important. If it doesn't do something, if there's no mechanism for it to affect our customers, they don't want to pay for it. So you have to think through, like, how are the results of our brilliant modeling that we're doing going to actually matter? For us, because we work in a streaming environment, that means fully automated and having our models running in production within that streaming environment. But you can get away from, and this is why they fail, right? Every time as I'm talking to data scientists, number one question I get is, how did you guys get your stuff into production? So the other space, I think, for data scientists are people who are more internally focused, not developing a product, but analyzing the business and running analysis and thinking about how to make decisions within the business context. And I see a lot of angst there too, where people struggle, where they say, I think the kind of oft repeated lament is, I put all this data together, I did this big analysis, and then the executive who asked for it just ignored me and went with his gut anyway. And I see this a lot, data scientists saying this, and the mentality is like, ha, look how stupid these executives are. They want to say that they're data driven, but they can't actually follow the data where it leads. And I think this is fundamentally a problem with data science and with our approach to data science. Yeah, that executive may not actually be open to changing his or her mind based on the information that you can provide. That means you shouldn't have undertaken the project. So you have to think ahead of time, what will this data be able to show? How will my analysis, what will I be able to come up with? And you need to make sure that the outcome of that is actually going to have an impact. You have to think through. And then the executive is going to change his or her mind or do something that's contrary to the other information that they've collected or from their experience. If you can't figure out how to connect those dots in a way that's going to happen, it's on you that at the end of the day, they're not satisfied. I also see this because I'll oftentimes see analysts and data scientists fail to come to a conclusion. So we don't want to put our necks on the line, or we don't feel like we have the context to make a final decision. And that means that we just put out there, data, and then we expect that executive to synthesize it. I think data scientists have to use a lot of executive thinking. We have to be able to think about the context in a broader sense than just the data that we're looking at. And I think this is why the dashboard proliferation is a lot less fulfilling than many data scientists have hoped that it would be. We go put out a zillion dashboards, and we put more and more data on those dashboards. And yeah, somebody looks at them, maybe they like looking at them, but if you haven't thought through what they're going to do with that information, how is this actually going to change the world? And I don't mean that in like, we're all going to change the world, end world hunger or something, but I mean, what is the impact going to be? What direction is going to change for the business? If you can't answer that about the data that you're putting out, then you're just doing what I wanted to do, and you're trying to put out another score and hope that this time, now that we have 3 scores, we're going to be more impactful than when we had 2 scores. And this is why I think that realizing that artificial intelligence occurs at, it is an impression at the human interface, why I think that's important. You have to realize that it's not about your technology, it's not about your data, it's not about your science. You have to think about the result. This is why climate scientists can't tell us what to do about climate. And public health officials who are looking to epidemiologists, there's no answer from science. Science can't tell us what policy to take, can't tell us what to do. It can tell us about the impact of what we are doing or what we might do. But at the end of the day, policy decisions also have to take into account the context, other externalities, other impacts. And that piece, that's what's fundamentally missing from most data science. So Andrew Ng has been in the news a lot lately. The last month or so, he's been talking a lot about ML ops, which I think is largely a positive development. And specifically, he's saying we need to become more data-centric rather than model-centric. And he is correctly, I think, attacking the idea that we should put our effort into tweaking models. He's done some case studies that show that if you have a limited amount of time and you spend that time trying to improve your model, you won't get you won't get as much improvement as if you spend that time trying to tweak the data. That's healthy. I think that's a good way of thinking about it. But my answer is to this question I posed here is neither of these things. I think you need to be problem-centric. So assuming that you can go clean up the data and that's going to get you your benefit, it assumes that you've already understand the problem very well, and also that the data that you have available is the best data to solve that problem. So I have a common approach here, and I'm not trying to knock this approach. This is how we put the OmniScore into production at Count. So I'm getting into the part here that's going beyond like, don't fall on your face at the very beginning. This is getting into how do you get from being effective to being extremely effective implementing artificial intelligence. So the traditional approach, I think, again, it can be successful, is you have your data scientists driving the beginning of this process and identifying opportunities. You have cross-functional teams because you have to be able to deploy this stuff. You have to have an impact, that action stage. Go into product architecture and think, how do we build a product around the kernel of technology that the data scientists have come up with? That leads us to thinking data, features, pipelines, apps, building out all of these things. And then applying it to real world problems, and then thinking through what that application looks like in terms of customer experience and how you support the rollout of this to your customers. Again, we found success with this approach at Count. But the better way to do this is to turn around this process. So you notice all the boxes here are backwards. Starting with, again, because AI is experienced at the human interface, thinking about how the customer is going to use the solution that you're bringing in, what problems that they are facing in the real world. That should then drive what is the data that we need to address this problem, what features should we be extracting, the pipelines, the apps, and then thinking about how we're going to architect the product before taking it to execution. And then the data scientists here actually live largely at the end of this process, because now you can do what Andrew Ng is saying, and you can bring a problem to a data scientist where they have the data, and then you're asking them to apply the model to address this problem. But it has to start and be focused on the customer, who again may be internal. They don't have to be an external customer. So since I'm just knocking on Andrew Ng, now I'll say something where he really helped me out and build him back up a little bit. Andrew Ng put out the AI Transformation Playbook, which basically tells you how to put together an AI strategy for your business. I was developing an AI strategy and found this and found a lot of things that resonated with me. His steps are essentially execute the pilot projects to gain momentum. Sometimes people call this the low-hanging fruit. You got to be really careful with this step, because if you get stuck delivering low-hanging fruit, you'll never deliver the high value that people are looking for from expensive data science teams. But it is where you start and get momentum. You have to use that to build your team up. And then this is, I think, the most important thing on here, to providing broad AI training. A little bit back, I said Google cannot get to artificial intelligence through the search bar. No matter how good an AI team sitting in a corner somewhere developing a recommendation engine, no matter how good that gets, it will not be AI as long as they are going through that search bar and we're stuck interfacing the way that we would talk to a computer instead of the way that we would talk to a person. So you have to go and make a transformation of your entire business. You need to have your executives speaking the right language. You need to have your sales team speaking the right language, your customer team speaking the right language. So we had a score, that supervised machine learning score that predated the OmniScore. We put it out and we had some good success converting customers, but we were frustrated that we couldn't get broader adoption. We went around and looked and said, people should just be using this score. And instead they have 40 or 50 rules to find fraud. And again, we want to blame the customer. We want to say, why are they doing this? It's stupid. They should know better. Let's try to convince them otherwise. When we actually looked at how we got to that point, we realized we were onboarding our customer default rule set that had 20 rules in it. So we were training our customers to think about our solution as, I need a whole bunch of rules to find fraud. We were not guiding them towards the transformation that we had made on the technology side towards delivering a decision. And then taking a step further back, our entire sales process emphasized setting policies and writing rules within our tool, rather than emphasizing the strength of the machine learning solution. And as I said before, showing the value of that, providing some proof points. So we did not have success with our technology until we had success within the rest of the organization in taking this mindset of an AI mindset. The idea that we're not just providing a tool here, but we are automating a human process that our customers, our customers are doing manually currently. We are automating that. It's an AI solution. That took a lot of training and, frankly, a lot of learning, because as the data science and artificial intelligence group, we're looking at how do you go and sell this up front? How do you go and set up a simple rule set that's based on machine learning that works well, and prove to ourselves and to our customers that it does work well? You also need to develop an AI strategy, and then, very importantly, also the communications, both internally and externally, around this. Another view that I find helpful is the AI maturity model from Gartner. Gartner has these maturity models for everything. This is how you make money as a consultant. You come up with a nice model and then you change the words out for every little area. That being said, I do find this valuable. Level 3 operational. When I was looking at this in 2019, this is where Count was. We had AI in production, creating value, like process optimization or product service innovations. So we had a product, we were selling it, and we were making money with it. And we felt really good. Like at that point, at level 3 operational, you can see it up in the upper left. This was a text out of the source that I have down there. At least one AI project has moved to production, and best practices and experts in technology are accessible to the enterprise. AI has an executive sponsor and a dedicated budget. Like, that is a huge accomplishment. And we had worked for years to get there. And so it very much felt like the top of the pinnacle, at least from my perspective at the time. But then you look forward at what the next steps are. Systemic. AI is pervasively used for digital process and chain transformation and disruptive new digital business models. All new digital projects at least consider AI, and new products and services have embedded AI. Employees in process and application design understand the technology. So again, outside of just the technology group, AI-powered applications interact productively within the organization and across the business ecosystem. So that was another step in front of us. And you can see the difference here that I'm talking about you can hit operational, largely within the technology group. If you want to get to systemic, you have to go and convert the rest of the operation, the rest of the business. At Count, we've now accomplished, I think, level 4 systemic, and Gartner doesn't really define level 5, where AI is part of the business DNA. But I think arguably that we've been able to achieve that as well. You go to our website now, we actually used to have a lot of focus on AI. And I think that we've actually matured past that to where you can still see AI is an important part of our story. But we're now emphasizing the specific techniques and approaches that we use within that AI space, which is showing a level of sophistication, in this case, from our marketing department, that they understand not just to go say AI a whole bunch, which used to work pretty well, but now understanding that we have to go in and provide more of those proof points and the detail about how we're doing it. But in many ways, for a while, we were self-consciously focused on the AI messaging. And now we've moved beyond that because, again, it's moved into our DNA where that's just part of the expectation. We all understand that we're delivering automation and human-like judgment with better than human results. The press release when we sold this year for $640 million, I was very pleased to see that the definition of Count, the kind of one sentence definition there, was a provider of artificial intelligence driven fraud prevention and digital identity solutions. So again, that's, I think, the level of the success in that transformation, and the fact that the rest of the business was comfortable making these claims and understanding what it meant. So to summarize, I hate when people put conclusions and then actually just summarize. So here's the summary. Frankly, I also hate when people just summarize instead of giving the conclusions, but whatever, you get what you get. AI is defined at the human interface, and that makes it a useful organizing principle that gets you focused on the customer and the user rather than talking about the technology, especially in compared to machine learning. You don't want to sit around talking about your tech. You want to talk about the customer and what it does for them. Data, models, tech, that's the means. They're really important. You got to have smart people who know how to do them, but nobody cares. Automating the solution, that's the end. And you should start with the end in mind. You need to know what you're trying to accomplish, because solving for a general artificial intelligence solution is, as we all know, a pipe dream. But solving for specific, narrowly defined problems that have high customer value is achievable with the technology that we have. And that's what I've got, and I'm happy to answer questions. So I hear that you can hit a button somewhere in the upper right if you want to talk. Otherwise, you can type it into the chat. All right. Well, barring anything else, then I'll assume that I've either answered all of your questions or talked everybody off. Oh, Nate has something.
Can I ask a question?
Yeah, just be loud.
What advice do you have for data scientists who want to be more engaged with like the product thinking, and understanding how to deliver customer value, thinking about taking a more problem-centric view? Like, what steps can an active data scientist take to start with the problem more rather than the data or the model?
Yeah, I think that's a great question. So this is a reason I'm kind of skeptical of the programs that are turning out a data scientist in 18 months and teaching people how to do just the modeling. I think that you need to have executive level thinking in data science. One of the ways we look for that here is we look for people that have strong research experience in a good academic environment, or in a very research-oriented private sector situation. So, the research process is seeing a problem and asking questions that help you understand aspects of that problem to get closer to an answer. I think that done right in the research environment, in kind of more of a pure applied research scientific environment, can be good preparation for that. I also think that historical MBA programs that focus on analysis, it's one of the reasons we see so much business intelligence and data analytics coming out of the business schools, because the amount of data that someone can use is different now, but the method of thinking is not different than they've always taught executives to think. And then, so that's, I think, training. And then when you're actually sitting down to do this, I believe that you have to understand what you're trying to automate. So again, we have this idea, it's machine learning. I don't need to be a domain expert. I'm going to take some data, I'm going to see what the model says, and then I'm going to get an answer. I just have never seen that actually work. I think if you can't sit down and do the task that you're trying to automate, I don't think that suddenly the computer is going to be smarter than you are and it's going to be able to do it. So that doesn't mean you need to be a domain expert in everything, but it does mean that your first step needs to be to become a domain expert in your area. So when I came to Count about 5 years ago, I knew nothing about credit card fraud. And that was where I just embedded myself at the beginning. See Rich Stuppy, in here, Rich, who hired me into Count. Thanks, Rich. He and I spent a lot of time talking about this, and I spent time working with his team to understand what it is that we're actually trying to do and how we're trying to do it. And then the next step is figuring out how to automate it and apply the tools that we have. So a lot of time spent with requirements. Don't just jump straight into, let me see what I can get out of a model. Rich is asking, what advice do you have for executives to better interact and deliver value from the data science work? So flipping that around and kind of getting at the other side of that. I think that, I don't normally advocate for consultants, but I think that this is a place where if you're trying to add a data science function within your business, it's helpful to make sure that you actually have a problem that can be automated. That's the biggest question you've got to ask. There's certain characteristics you need to see. You need to see high touch environments, tasks that are somewhat constrained, that don't have a whole lot of ambiguity or uncertainty or a lot of new patterns. Machine learning is always inherently backwards looking. So there are some technical requirements that make some problems easier to solve than others. And I think you need to understand that before you go hire a whole bunch of people to address it. And then you need to realize that you're developing a complete cross-functional solution. So you need to have not just data science, but the engineers to productionize the results of what you're looking at. And then that action part, I do put some of that on the executives. You need to be ready to run with the results of what your team is going to bring you. And then if you already have a developed AI team and you're trying to figure out how best to use them, I think that you need to break down, and this is getting now past just that operational level, getting to how you put the sophistication on the end. You need to get away from thinking about artificial intelligence as a separate function of the business. It should be integrated in everything that you're doing. And so you can't be afraid to go in and get involved with the, with that technical team. And I'm going to regret saying this to Rich, but putting requirements on that team and making sure that you're representing the customer and enforcing, this is what the business needs, and don't buy the, oh, well, we've got smart people thinking about this and I can't go in and understand it because it's fancy technology. Fundamentally, you're asking them to automate your customers' problems. And if as an executive, you don't know what that means, then you're probably not a very good executive for the job that you have. You should be able to be that customer advocate. Joel says, what advice do you have for product managers with customer problems they believe AI and machine learning can solve? I think this is kind of in this same space. I've talked to a lot of product managers who say, hey, I have this problem, I really want to apply machine learning to it. And oftentimes it's just not a good fit, especially if you don't already have a team that can do it. So again, I would reach out and talk to people who understand the technology and whether that's a consultant or whether that's just reaching out to, one of us in the community here. But I'm skeptical of a lot of the things that I have heard just turn out to not be great ideas for automation. If it is a great idea for automation, then if you looked at I'll go back to this thing. If you look at this step here, the more that you can do to understand the customer problem and define it clearly, and understand the constraints in terms of what data you might be able to get for somebody, taking that into the conversation with a data science team, they're going to love you for that. Like, data scientists don't like the ambiguity of, hey, we sort of have this problem, we don't really know the edges of it, but we want you to solve everything that we've ever run into. They like clarity, and particularly if you also have data, they like that. How would you create collaboration between your AI team and the rest of the company? So I can tell you how we did it at Count. I don't know how to abstract it because I've only seen it happen once. But the way we did it at Count is we had a lot of success. So I think it's important to see those steps of maturity, and don't look at it and be like, oh, we want to be at level 4, we want to be at level 5. Go back to the maturity steps here. You have to start at 1, and you have to go through each one of these steps. So you're not going to go convince the entire business to change the way they're thinking about the problem and the way that they're delivering customer value, unless you have gone and built some products that are getting real traction. So I feel very blessed at Count that our executive team saw the value and made this transformation in the entire business to how we think about delivering our product. I'm not sure we deserved it, frankly, based on the value that we had shown, but it was, but the point is that it was based on success that they could see. So I think you have to just realize, like, you have to take each one of these steps, and it is hard. When we were looking at, again, 2 years ago, I was writing a strategy document, and I'm saying I need to get, and this comes out of Andrew Ng's playbook, but I'm looking at it going, I need to get 4 hours with each of the executives to train them, and I need to get 12 hours with most of the engineers to train them, and I need 40 to 80 hours with a specialized group of machine learning engineers to train them. That's a big ask, and I didn't think we were going to get it. I'm still kind of frankly surprised that this all worked, but you have to just go. You have to just go and keep pushing on it and keep showing the incremental value along the way. And then Rich says, can you explain the difference between good data and a good supervisory signal? So this is a really tough place in machine learning, is that right now most of our techniques are supervised. So you have to have outcome data. And back to the question about how does a product manager deal with this, I would say many of the problems that a product manager will come across, the limitation is going to be that there's not a supervisory signal. So there's not good data to go and train a model with. That has never bothered me. My team here will tell you that I'm anti supervised models, and that's not because they don't work. They work really well. I just think that in most cases, you can capture most of the value of that supervisory signal fairly quickly. And so then the real question is, what next? And this is what I mean by, you need to be able to really well understand the problem or be able to see the pattern in the data. So supervisory solutions use the past outcomes. Unsupervised solutions look for patterns and structure within the data. I'm big right now on a lot of graph approaches. I think that there's a lot of information that's present that you can extract by looking at relationships within data. A lot of those approaches are unsupervised, but you go back to when I was working on self-driving cars and how we were not using machine learning there. You have to just really understand what the hell you're trying to do. What are all the steps of driving? And how do you design a set of behaviors that accomplishes all of those things with minimal complexity? That is very product-oriented work. You're breaking down a problem and thinking about what components, what it takes there. So I tend to like, I think a lot of the opportunity right now is in problems that don't have good supervisory signals, because I think people have already solved a lot of the ones with good solutions in the supervisory space. So I think you want to really find problems that somebody hasn't tried to solve before and understand them well and break them down, figure out how to do it yourself, and then figure out how to automate it. Any advice on the transition beyond low-hanging fruit tasks? Yeah, do it as soon as possible. So I believe strongly that it's easier to change the direction of something that's moving than it is to get it moving in the first place. So multiple times here at Count, I've stood up new teams. And the first thing we look at is how can we get this team functioning? And we usually start with a project that obviously has some business value where we wouldn't do it. But I usually don't really care about the business value. Like, I'll have written off the business value before the project starts. We're doing a cloud transformation right now. And at the beginning of the year, we set out some goals for what we wanted to have done after 3 months. But I was clear with the team that if all we had after 3 months was our teams formed and executing well, I would settle for that. And I would prefer that over delivering the specific milestones that we had signed up for. Now, turns out we got both, which is always the best choice. But like, that's what you have to realize. You have to realize that the purpose of the low-hanging fruit is just to get your team formed and to start building stakeholder relationships, which means once those things exist, you don't have any value in low-hanging fruit anymore. Or you do, but it's just low value. All right, I think we're out of questions. I know we're out of time. So unless anybody's got anything else. Thank you very much. And if you want to reach out to me, my email address is josh.johnston@count.com, or you can find me on LinkedIn. And I'm happy to talk more if you've got questions that come up later.